Hello everyone, welcome to this video. On this occasion we are going to solve the Schrödinger equation as much as we can before we are actually given a potential. So, well, let's get right into it. So we're going to be using a method to solve this partial differential equation that is quite common in partial differential equations, which is just the separation of variables. So what we are going to try to do, in case you have never encountered such an equation before, what we want to do is we want to take this psi. Here I wrote this big psi. This is a function of the coordinate position and time, and we want to now define this as the product between some function lowercase psi that is only a function of x times another function that is only depends on time. And we're going to be looking for solutions that are of this form. Obviously, not all solutions will have this form, but as we will see, this kind of solution will be of very much a lot of interest, and you will see that we can actually form the other solutions from these ones. So, but that is getting ahead of myself, so let's just begin doing this. And what we're going to do, and that's why it's called separation of variables, is that we want to take all of the x to one side, all of the t to the other side, and well, you will see how it is that we proceed. So let us now replace this into our Schrödinger equation. So we get I h bar, instead of this partial psi, we get partial of psi of x times f of t with respect to t. But here, this psi of x does not depend on time, so we can actually just take it out, and I'm going to rewrite this, and we can just put this psi of x in front, and we get partial of f of t dt. So this is going to be equal to this right hand side, which is just minus h bar squared over 2m. Now we get this, in this occasion you will see something very similar to before. Instead of this psi, we write down this lowercase psi times f, but only this psi of x depends on x. So we can just leave this f of t multiplying over here. And then we got this other, the potential term, which is just going to multiply psi of x times f of t. So this is a very typical first step for this method. Step number 2, we're going to divide by both psi of x and f of t. And this is done obviously to separate the variables, as you will see what happens now. So I h bar, this psi of x is going to cancel out. We're just going to be left with this partial differentiation, and this is going to be divided by f of t. So this will be equal to minus h bar squared over 2m plus, now in this case the f of t is going to cancel out, so we just get 1 over psi of x times this, whoops, I almost wrote down an f there, it should be a psi of x dx squared, and here this potential term will be left alone. So in this, now as you can see, we got on the left hand side only things that depend on time, and on the right hand side only things that depend on x. This potential can depend on the coordinate x. I didn't write it out explicitly, maybe I should have, but this potential can depend on x, and it usually does in some way. So what we do next, and this is the crucial step of separation of variables, and that's why it gets the name, we say, okay, since the left side only depends on t and the right side only on x, if you were to integrate this or derive it with respect to the other variable, for example, this thing on the left, if you were to derive it with respect to x, it would be 0 because it doesn't depend on x. And the same thing to the right hand side, if you were to derive this with respect to t, it would also be 0 because it doesn't depend on time. So, and just a little note, I didn't mention it before, but the potential will only depend on x basically in the entirety of this course. which I'm, by the way, basing on Griffith's textbook, which is just amazing. It's very good. Obviously, I'm going to be taking things from elsewhere too, but I'm taking the main structure of the course from Griffith's book, so you should check it out if you have any questions. You can also comment them, of course. Well, as I was saying, each side is going to be constant to the other side, at least to the variable from the other side. So what we can do is we can say, well, then each side is going to be equal, and it has to be equal to a constant. So we're going to just name it, say this is equal to e. This is just a regular step in separation of variables, because, as I said, each side only depends on one variable. So when you see it from the point of view of the other variable, it's going to look like a constant. So having seen that, we are going to split up this into two equations, and that is the basis of this method. We want to go from one differential equation that depends on two different coordinates, so a partial differential equation. We want to go to two ordinary differential equations, which are much easier to solve. So in this case, what is it that we had? We had IH over f of t df. Well, in this case, we don't need to write it as a partial differential. There we go. This is supposed to be an f, by the way. I'm going to write it better. Okay, f of t dt, and this is equal to e. All right. So now what we have to, well, this is normal to solve, but let's first write down the other equation, which is just minus h bar squared divided by 2m. This is d squared psi dx squared psi plus this potential plus potential x times psi. This is psi of x, of course. This is equal to e times psi of x. Here I multiplied by this psi of x that was in the denominator. Okay, so now we got these two separate equations. So let's begin by solving the first one. This first equation, I hope you don't have much trouble with it. This is a regular differential equation. You can here just separate the variables and just integrate. So you get df of t over f of t. This is equal to e divided by ih, which is the same, and I like this better. Dt. I like it better as minus I e divided by h bar times dt. So now we just integrate. To the left, this is just going to be the log of our function f of t, and to the right we are just going to get minus e I e t over h bar plus some integration constant, and finally we can just exponentiate this, so the log will cancel out, and we get that f of t is going to be some constant a times e to the minus I e t over h bar. And this is the solution to the time part of the Schrödinger equation. And this constant a we can just absorb into the constant that will come from the radial part, from the x part, because remember this psi, that is our wave function, is going to be little psi times f of t. So if this f of t has an a, which is just a constant of integration, and psi has some other constant of integration b, we can just absorb this a into b, because any number times any number is still just any number, so we can just absorb it into that. So this is our first solution, very important. I'm going to now erase this a, by the way. Okay, so this tells us how this system is going to be evolving with time. This is very important. And the other important result is this equation right here. We cannot solve it if we do not know what the potential is. So that is what we're going to be doing in the future. In future videos, we're going to be just taking some potentials and seeing what the solution is for this equation. So that is the solution for the Schrödinger equation. Now we need to discuss a little bit further about these solutions. So what exactly is the point of these solutions? What can they tell us? There's three important things. First is that these psi of x, these small psi of x, these are stationary states. Okay, stationary states. So what this means is that these are just fixed, they're not moving, and that makes sense because the temporal part is this f of t. Remember, the wave function is a product of this smaller psi times this temporal part. So if we don't take the temporal part into consideration, you're just going to have some stationary state that just moves, and as you can easily check, the expectation values are also going to be stationary, they're not going to be changing. And you can also see that its normalization is going to continue being the same. It all comes from the fact that if you do this integral of this big psi, right, this is just the probability dx, what you get here is, remember, this is going to be some psi of x, small psi conjugate, times psi of x, and you're going to have this 2e to the plus, because it's conjugate, I e t h, and then I to the minus I e t h bar. So these two are just going to cancel out. It's just gone. So the temporal part cancels out. That's why they are stationary states, and it will make more sense when we can finally see some examples. We have been just doing a lot of theory for now, and we will get into some more practical examples. But this is the first important part. The second important part is that these states, this stationary state of a small psi, and it's important to note we will be referring to this small psi as the wave function, even though it is not really the wave function, because the wave function is this big psi that also has the temporal part in it. But we will be dealing so much with this little psi that we're just going to be calling it that way, and we just have to keep in mind that the actual wave function is going to be this big psi. Okay, so as I was saying, the second important thing about the states is that they have a definite energy. Okay, and you can see this, and as you're going to be seeing, because we saw this Schrödinger equation comes from this Hamiltonian operator that is going to be applied on our wave function. In this case, it's just going to be little psi, but as you can see, it's the same in this case as the big psi. So when we apply the Hamiltonian operator, it's usually pi squared over 2m plus this potential. But if you take the form of the operator, as we saw in previous videos, we just get this regular form of the Schrödinger equation, dx squared plus v, and all of this applied in on this wave function. But this is exactly what we had over here. So we can just instead write this is just e times psi. Now you might remember we already saw this, at least I'm going to write it again here. We already saw this form during the first video where I introduced the Schrödinger equation. I also used it to derive the Schrödinger equation, but here you can see where it comes from. This is also why we named this constant E, because this term is the energy. When you apply the Hamiltonian operator on a system, you get its energy. That's why we called the constant of separation E, because we knew that we were at least, once you know that it's the energy, it makes sense to call it E. So if you're teaching, it's good to already call it E. Okay, so now let us look at the expectation value of the Hamiltonian. What do we expect to find here? So this is just going to be this psi dagger, psi conjugate times the Hamiltonian applied on the wave function. But what is the Hamiltonian applying on the wave function? This is just going to be, as we see from this Schrödinger equation, this is just the energy acting on the same function. So we can just take the energy out. The energy is just a number, so we can just take it out of the integral, and we get this integral over here, which I hope you can recognize. This is just the probability of finding the particle anywhere in space, which is just 1. So the expectation value is just going to be, whoops, that square, I don't know where I worked at. The expectation value of the Hamiltonian is just going to be the energy of the system, which is what we hope to get. So what happens now with the squared, the expectation value of the square of the Hamiltonian? Now, in doing the same as before, we can see that the Hamiltonian squared is basically the Hamiltonian of the Hamiltonian, multiplying here. So this first term is going to be just E times the psi. So we get psi conjugate Hamiltonian times the energy times the wave function. We can take the energy out as we did previously. And now we get once again the Hamiltonian acting on this psi. So we get another energy out. We get energy squared times psi conjugate times psi dx, which is once again 1. So the square of the expectation value of the Hamiltonian squared is just going to be E squared. So why did I do all this? The whole point of doing this was to take a look at the standard deviation. What is the standard deviation of our Hamiltonian? Remember, this is just going to be our Hamiltonian, the expectation value of the Hamiltonian squared minus the expectation value of our Hamiltonian squared. And we take the square root. Well, it doesn't really matter if we take the square root in this case, but since this right here was the energy squared, and the second one here is the energy, and we have to square that, this is just going to be 0, which is why I was saying that it doesn't really matter if we have the square root, because it's still going to be 0. But what this means is that there is no uncertainty in the energy here. In stationary states, because they are stationary, they are not moving, we know what energy we will get if we perform an experiment on it. Okay, there is no uncertainty. That's why I said they have a definite energy. Now, the third thing that we have to take into consideration, and with it we are going to be ending the video, is that these states, these psi of x, as I said, they may not be the best solution. We said only some of the solutions of this big psi, right, of x comma t, are going to be of the form small psi f of t, right? But as we will see later on, when we can see more of the mathematical formalism, we will get to that. But for now, I just have to tell you what it is. As we will see, these solutions, since they are solutions of the Schrödinger equation, they are also orthogonal to one another. So what I mean is that solutions from one energy state, so let's say we got some state, this is the big psi, some state which is just going to be some wave function 1, and we'll have some energy E1, and we will also have some other states, e to the minus I, e2 t h bar. Since they are all solutions to the Schrödinger equation, their sum will also be a solution to the Schrödinger equation, and we can have n amounts of them, up to some term phi n e to the minus e psi n t over h bar. So what I want to say in this point is that although these solutions may not be all that useful by themselves, since they are solutions and they are orthogonal to each other, also we will prove eventually later on that they are orthogonal and they are a complete base. So this means that you can write down any solution, not just these simple ones, as a linear combination of these simple solutions. And that is extremely useful, because solving this is way easier than solving some other form. So this right here is going to be an extremely important tool. So with this, we are going to conclude at least this third part that was very theoretical, because in the next video we can finally begin solving the Schrödinger equation for a given potential. We will begin with the infinite square box, and because this was just in general, we couldn't get to the solution of the x part without an actual potential, but we will now finally begin doing that. So I really hope that you enjoyed this first part. We will now begin doing something that is, I hope, more fun, more practical. So if you got any questions, just let me know, and I'll see you in the next video.